This is Physics 104B homework for Porterville College, Chapter 16. We start with number 17. At what temperature do Fahrenheit and Celsius scales coincide? Okay, so this is just a little algebra puzzle right here. Here's a conversion given in the book that Fahrenheit temperature equals 9/5 Celsius temperature plus 32. Question is asking at what temperature are both of these equal? So let's just make temperature Fahrenheit and temperature Celsius be the same variable. I'll call it x. So we're solving for x. So x equals 9/5 x plus 32. And just solve that for x. We can have x minus 9/5 x on the left-hand side, which becomes negative 4/5 x equals 32. Solve that for x, and you should get negative 40 degrees. And you can check that by looking on a thermometer that goes down that low, and you can see the Fahrenheit scale and Celsius scale match up at negative 40 degrees. Number 26. How much heat does it take to bring a 3.4 kilogram iron skillet from 20 degrees to 130 degrees? And then it asks a question about the time. Okay, so the heat to raise a solid's temperature, heat is Q equals mc delta T. So there's the mass, times, you have to look up the specific heat, C of iron, that's 447 joules per kilogram Kelvin. That's given, that table is given in chapter 16. And delta T, final temperature minus initial, 130 minus 20 is going to give 90 Celsius degrees. Plug that in, you get 167,000 joules, but I'll go for rounded to two significant figures, so 1.7 times 10 to the 5th joules. Part B gives the power, and we have to figure out the time. So if power is heat divided by time, we solve for time as heat divided by power. I'm going to use not the rounded off version, but the exact version my calculator gave me for question A. Divide that by the power, 2,000, and it says watts, but I'll turn that into joules per second. And so we get 84 seconds. Number 28, find the heat loss rate through a slab of wood and a slab of styrofoam. It gives the thickness, 2 centimeters. It gives the two surface temperatures. When you look at the formula, you'll notice that what's missing is the area. Area is not given, so what we can do here is solve, rather than for H, the rate of heat flow, let's solve for heat flow per square meter. Or another way to think about that is to say, let's just pick an arbitrary area and let area be 1 square meter. But as you see right here, I'm solving for H over A. Now, the formula, often when I use this formula, pretty much every time, I'm just taking the absolute value. So you notice I've gotten rid of the negative sign. Negative sign just refers to that it's the opposite direction of increasing temperature. But you already know that. Heat will always go from high temperature to low temperature. So that's why you rarely see the negative sign when I write it. Okay, so with that in mind, we're solving for H over A, heat flow rate divided by area, becomes K delta T over delta X. For wood, we have K of 0.11 watts per meter Kelvin. You can find that in the table in chapter 16. And what we get is 110. Now, H is given in watts, but we're doing H over A, so 110 watts per meter squared. Styrofoam has a much lower K, 0.029 watts per meter Kelvin. And by the way, that K is thermal conductivity. So what we get is 21 watts per meter squared. Styrofoam is a good insulator, much, much better than the wood, so you see it's got a lower rate of heat flow. Number 29 applies this concept to a steel slab, a steel stove, measures 90 centimeters by 40 centimeters and is 0.45 centimeters thick. The inside surface of the stovetop is 310 degrees Celsius, outside is 295. Okay, so here it is, 295 on the top, 310 down below. You can see the heat flow is going to go from the hot to the cold. Here's all the relevant information. We need the thermal conductivity for steel, 46 watts per meter Kelvin. The thickness is 0.45 centimeters, or times 10 to the negative 2 meters. The area is 0.90 meters times 0.40 meters. So when we solve for the rate of heat flow, Ka over delta Ka delta T over delta X, we plug in those numbers, as you see here, and you should get 55,200 watts, which I'll round to 55 kilowatts. Number 30. How thick would concrete walls have to be to have the same insulating value as 2 inches of styrofoam? The point here is to show what an excellent insulator styrofoam is, as opposed to just concrete walls. So how thick does the concrete need to be to match the insulation of the styrofoam? Well, the basic formula, H, rate of heat flow, equals Ka delta T over delta X. We're going to assume that we're looking for the same rate of heat flow between concrete and styrofoam. So let's say H of concrete equals H of styrofoam. And then we plug in the values for H. So on the left-hand side we have concrete, on the right-hand side we have styrofoam. So we use the Ka delta T over delta X. Let's divide out the things that are equal. So we're assuming everything's equal about the area. The surface area is going to be the same. Same wall that we're dealing with. Delta T is the same because we're looking for whatever the outside temperature is and the inside temperature is. We want it to, it's all the same. So what's left, what we're comparing, is the thermal conductivity of concrete divided by the thickness of the concrete equals the thermal conductivity of the styrofoam divided by the thickness of the styrofoam. We're solving for thickness of the concrete, delta XC, and it becomes the thickness of the styrofoam times the ratio of the thermal conductivities. So 2 inches times, then you look up those thermal conductivities in the table, 1 for concrete, divide by 0.029 for styrofoam, which becomes 2 inches times, and that ratio is 34.48. So it becomes 69 inches of concrete. That's 5 feet, 9 inches of concrete would have the same insulating value of just 2 inches of styrofoam. Number 47. Let's see. So power equals heat divided by time, which means time is heat divided by power. For heat, we'll substitute in mc delta T for raising the temperature. So the time is going to be mass times specific heat times change in temperature divided by power. Plug in those numbers. Now mass, I got 0.330 kilograms. If you don't see that right away, just hold on. In the pink down below at the bottom of the screen, I show how I get that. I'll come back to that in a minute. Actually, let's do it now. Let's just do that. The problem says 330 milliliters of water. So here's some useful things to know. First of all, that a milliliter in volume is equal to a cubic centimeter. Now, I want to know what is the mass of 330 cubic centimeters of water. Well, mass equals density times volume, because density is mass over volume. So mass is density times volume. Density of water is 1 gram per cubic centimeter. Times the volume, 330 cubic centimeters. So we're looking at 330 grams, which is 0.330 kilograms. Okay, so that's how I got this mass, 0.330 kilograms. Times specific heat of water, 4184 joules per kilogram Kelvin, times the change in temperature. Change is always final minus initial. So 100 degrees Celsius, the boiling point of water, minus 10. And we're dividing by the power of 900 joules per second. So that gives us 138 seconds, or 2 minutes and 18 seconds. And 900 watt microwave oven, that's a reasonable what microwaves come in. And that sounds like about how long it takes to boil a cup of water. Number 55. Piece of copper, 300 degrees Celsius, dropped into 1 kilogram of water at 20 Celsius. The copper goes down in temperature tremendously. The water goes up a bit in temperature. So they reach equilibrium at 25. What's the mass of the copper? This is the conservation of energy problem. We are assuming, as I've taught you in class, that this is insulated, meaning the heat is not going to escape to anywhere else. So QC plus QW equals 0. That means the heat that goes into copper, and that's going to be a negative value because heat actually came out, but we define Q as heat going into a substance. So the heat into the copper plus the heat into the water equals 0. Now you don't have to arbitrarily make this negative. The fact that delta Tc, since the copper is going to cool down, this delta Tc comes out to be negative, and so this automatically goes negative. Okay, so we've got mass of copper, specific heat of copper times delta T of copper, plus mass of water, specific heat of water times delta T of water equals 0. Solving for the mass of the copper, that algebra, we get negative mass of water, specific heat of water, delta T of water, divided by specific heat of copper, and delta T of copper. Plug those values in. So we've got the negative 1 kilogram, 4184. Delta T of the water is 25 minus 20. Notice that that's a positive number because the water temperature increased. In the denominator, we've got specific heat of copper, 386. And this is what I was talking about a minute ago. Delta T of the copper, 25 minus 300. Be sure you're careful with the final minus initial. This comes out negative because the copper cooled down. So this negative and that negative are going to divide out, and you're left with a mass of 0.197 kilograms. And for two significant figures, we'll round that to 0.20 kilograms. '58 is another conduction problem. Instead of being a big slab of material, as I've drawn in the previous examples, this is a small slab. It's actually a rod, a long rod. Rate of heat flow is K times A, and here A is the surface area, the cross-sectional area of the rod. So with 58, we're given that the rod has a diameter of 3 centimeters. That means a radius of 1.5 centimeters. So the area is going to be this part here, pi times the radius squared, so pi times 0.015 meters squared. You've got your K, you've got your difference in temperature, 100 on one side, 0 on the other. And you're dividing by the distance, which is the length of the rod, 0.40 meters. I left the negative sign in there, but you'll see by the time I get to my final answer, I just disregard it. So 14.2 joules per second, which becomes 14.2 watts. Number 64. Power output of a microwave oven that can heat the water to boiling point in 2.5 minutes. Neglect the container's heat capacity. What that means is we're just going to assume that all the power of the microwave oven actually goes into heating the water. We had a previous problem where the microwave oven's power was 900 watts, and generally microwave ovens are going to be in the several hundred to 1,000, something like that. So we know what a reasonable answer will probably be. Okay, power equals heat divided by time. Heat is mc delta T, which is the raising of the temperature of the water. So we have the mass, 0.430 kilograms of the water, times specific heat, 4184, times the change in temperature, 100 degrees minus 20, divided by 2.5 minutes. We need that in seconds, so 150 seconds, and we get 960 watts. Okay, last page. Number 66. Now we get into some radiation problems. The star's surface temperature is 50,000 Kelvin, radiates 4 times 10 to the 27th watts. If the star behaves like a black body, what is its radius? Okay, black body, by definition, means emissivity is 1. So we're going to take this power equation, P equals E sigma A T to the 4th, and just get rid of E because we're letting that equal 1. Solve it for area. So we want to know the radius of the star. We're going to assume the star to be spherical. So A refers to its surface area. And we solve for that. Surface area is P over sigma T to the 4th. You've got your P given in the book. Sigma is the Stefan-Boltzmann constant, 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the 4th. And also in the denominator is 50,000 Kelvin to the 4th power. That gives us an area of 1.129 times 10 to the 16th meter squared, but we want the radius. So I'm turning the A for area into 4 pi r squared, surface area of a sphere. And so when I solve that for radius, so we divide by 4 pi, take the square root, and we get a radius of 3 times 10 to the 7th meters. Number 74, for a little bit of calculus fun here. In the book, it gives the specific heat of copper in the table, but that's for a certain temperature range. I think in the table it says this table is good between, for the range 0 to 100 degrees Celsius. Now this problem says, taking it to an extreme, at low temperatures, it's approximately proportional, the specific heat is approximately proportional to the cube of the absolute temperature. So for copper, it says C equals 31 times T over 343 to the 3rd power. And that's given in joules per gram Kelvin. So be careful of these units. Joules per kilogram Kelvin would be the MKS units, but this says joules per gram Kelvin, so we'll go with that. Integrate the equation, dq equals mc dt, to find the heat required to bring 40 grams from 10 Kelvin to 25 Kelvin. Okay, so just for fun, you don't need to do this part, but I just wanted to calculate to see what is the specific heat of these different temperatures at 10 Kelvin and 25 Kelvin. And so at 10 Kelvin, it's 7.7 times 10 to the negative 4 joules per gram Kelvin. At 25 Kelvin, it's gone up a great amount, 1.2 times 10 to the negative 2, which is about 16 times what it is here. So we're definitely dealing with a changing specific heat. So as it goes up from 10 to 11 to 12 to 13, Q equals mc delta T is going to require some calculus. So dq equals mc dt for little increments of temperature and little increments of heat. And let's integrate that. So the total heat, let me shift this up a bit here. The total heat is the integral of the sum of all the little increments of heat, which is the sum of mc dt. I'm going to pull out what I can outside of the integral, which is just mass. So mass times the integral of c dt. I know the writing's getting kind of small here, but I just have the limits of integration, 10 Kelvin and 25 Kelvin. And from here I just plug in the values. So C is 31 times the cube of T over 343. Now all these constants, I just pull them out to the side. So the 31, the 343 to the third power. So what I'm left with right here is M times 31 over 343 to the third power. And the integral is just T cubed dt, taken from the limits of from 10 to 25 Kelvin. So I integrate that, and the integral of T cubed dt is 1/4 T to the fourth power. So down here you see there's my 1/4. All these other constants, here's T to the fourth power, taken from 10 to 25. So when you plug in all that and you take your mass of 40 grams, you should get an answer of 2.9 joules. Now, I wanted to see how could we do this non-calculus for an estimate. Well, what we could do, and it's going to be a very rough estimate, is use Q equals mc delta T, but which C do we use? Well, at 10 Kelvin that's way low, at 25 Kelvin that's way high, so let's just pick the middle. The average of 10 and 25 is a temperature of 17.5 Kelvin, and that would actually be right, except for if this were a linear, if specific heat were linearly related, but it's not, so it'll be a crude estimate. So let's just apply Q equals mc delta T for that middle temperature, with specific heat at the middle temperature. And I got that 4.1 times 10 to the negative 3, and I got that by plugging into this original equation, times the temperature difference from 10 to 25, and I got the crude estimate of 2.5 joules, which isn't too bad, not too far off from the exact 2.9 joules. And that is the end of the Chapter 16 homework.